define an optical phenomenon called dispersion. We've actually already seen dispersion. And then we do want to talk about the formation of rainbows, and we really have most of our recent phenomena responsible for rainbows. Okay? Yeah, all right. So before we actually get into those objectives, I want to do a little bit of tidying up so I can just put some things together. So who is this? This is the rear view mirror, right? This is the thing that kind of, if you're driving the car, it sits right up here. And what type of mirror is this? A plane mirror? All right. So what I would like to do is take my laser beam and reflect it off of that plane mirror, right? And try and reflect that onto the screen. I think I'll be able to do that. How many dots should we see when I reflect it off of the plane mirror? Right, let's turn that into multiple choice. Let's turn that into multiple choice. So we can say choice A would be we won't see any dots at all. B would be we see one dot. C is 2 dots. D is 3 dots, and we can say E is just greater than 3 dots. All right, so take 15 seconds as I erase the other boards and be ready to raise your hand for one of those 5 answers. Okay, please raise your hand if you think that we will not see any dots whatsoever on the screen. 1. All right. Please raise your hand if you think we will see 1 dot on the whiteboard on the screen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm not sure that that's the rest of it. And I don't think Victoria actually wanted to vote for this one. She just felt that.
Yeah.
Nobody was voting for that. All right. Well, you're all wrong. Why would I even bring this out if we were just going to see 1 dot? I mean, why would I do that? That would be perfectly normal to see 1 dot. What is a mirror? What is this mirror? We said it's a plane mirror, but what physically is it? It's glass and like a painted on reflective coating on the back of the glass. All right. So let's see that, and then we'll talk about why it is that we see so many dots. So now that I've told you it's not 0 or 1, what's it going to be? 2? 3. That's boring. How many?
More than 3.
I see 4. Come closer. Yeah, those don't count. That's just reflecting off the whiteboard. No, I'm off. I definitely see 4. If you can't see 4, come closer because there's a dim. I see 5 now.
Told you so.
I don't have any free hands. Can somebody come up here and just point to where each of the 5 dots are? So show us the brightest one first, okay? And then, you see the 5th one on the left? Somebody with better eyesight, come up here. No, it's still there. It's just, it's really faint. I can see it very clearly from where I'm standing. Henry, it's to the left of the other ones that you're seeing.
Yeah, I know. But what?
You don't see it?
No.
You need to seriously get the optometrist. Alright, so there is a 5th one that apparently apparently my vision is better than your vision. But you see it now?
Yeah, actually.
Alright, so point to it.
It's like under that one.
Point to it.
Here-ish.
Alright. So 5 dots. And the brightest one was not at either end. What's going on? What, Kara? I still can't hear you. Dispersion? No. No. Not at all, actually.
Reflection.
What? Light is a wave? Okay. So?
It's also a particle.
Shruti? Mirage? Is that what you said? We were actually not starting the objectives until like 2 things after this, so no, it doesn't involve any of the new stuff we haven't talked about yet. Jesse? Diffuse reflection? No. No, this is very shiny. Alright. So it's reliant on the 2 different things that make up the mirror. Alright, so let me draw it, and I'm going to draw it kind of big. So here's the reflective coating that, as I said before, is just painted onto the back surface of the glass. and then this would be like the front of the glass. So everything in here is just glass, the protective glass, right? And then we have the kind of metallic coating painted on the back. All right? So this is the front of the mirror. This is the front side of the mirror. This would be the back side of the mirror. And the reflection happens here, pretty much. Questions about this being the mirror and the reflective surfaces on the back? And that's pretty much true for every mirror. Like any mirror in your house is going to have glass and then painted on stuff in the back. If you can get behind the mirror, you can scratch that like reflective paint off. You don't want to do that, or ruin the mirror, but you can do that. All right, so we have light from the laser. Let me use it. I'll use red since that's the color of the laser. We have light from the laser. Oh, I don't know, maybe incident like that. All right, and then what does it do when it hits the edge of the glass? I heard one person say it refracts. I heard one person say it reflects. And the third person says it does both. And it does both is correct. However, the vast majority of the light will refract. But Henry's right also, a little bit of it does reflect. Anybody know how much reflects? It's 4%, about 4%. That's true if we're going air into water, air into glass. That's based on like the relative difference in index of refraction between the two medium. So I didn't draw this very well. The law of reflection should be governing this geometry, and why can't I get that right? That's a little better. All right, so we get about 4% of the original. So if this is 100% of the light that's striking the mirror, we have 4% of it just never even entering the glass. And what are we going to see when that hits the screen? Dot. Right? That was one of our dots. Is that 4% right there? But 96% of it refracts into the glass. And then what happens when it hits the back edge of the mirror? It will all reflect. If it's a very good mirror, it'll all reflect. All right? And then it's the law of reflection that governs that. So I want to try and draw that in. All right, questions from anybody so far about 4% of the light reflecting off the glass, 96% refracting into the glass, and then essentially all of that reflects back into the glass. Any follow-up questions so far? Okay, what is the light going to do now? It's going to refract and reflect. Guess how much of it refracts? Like 96% of this will refract into the air, and it will refract so that it bends away from the normal. So maybe something like this. And then about 4% of it will reflect back into the glass. This is not total internal reflection. If we have total internal reflection, we have 100% reflecting off of the air. We have not exceeded the critical angle. All right? So this would be 96% of this 96%. What's that, 92%? 0.96 times 96. Can somebody help me out with that? I think it's 92. Might be 93. 92. So 92% of our original light comes out here. So which dot is that going to be? The bright one. Right, the bright one. All right, but we still have 4% of the original light that's back in the glass. What happens when it hits the back? Reflects. What happens when it reaches the air again? 96% of it will refract, and 4% of it will reflect back in. So, oh boy, what is 0.9? No, how do I do this? This would be. It's essentially going to be 96% of. It's going to be what? How do I figure out? It's going to be a little less than 4%, maybe 3%, 4%, something like that, of the original light. Let's say it's probably rounds to 4%. Let's just call it 3% so that it doesn't look like we counted for everything. All right, it'll reflect again, it'll refract, whatever. How many dots do we have so far? That's enough because that's probably all you're going to see if I don't turn the lights off anyway. Right, yeah, 3 dots. Boom. The 4th and the 5th are too dim for you to see with the lights on and with you sitting where you are. So the one all the way to the right would be this one. The bright one in the middle would be this one. And then the one on the left, which is approximately the same brightness as the one on the right, is this one. And yes, there are smaller amounts of light that bounce around a few more times and then come out. Questions about seeing the multiple dots with a plane mirror? Yeah.
How would you differentiate between the side of the 4 and the 2%?
How do I differentiate between these two sides?
Yeah, like when you were showing the
Yeah, so the 4%, when we had more, with 3 dots, I probably can't do it. With 3 dots, I probably actually don't know which one is which. But with 4 dots, now I've got 4. I don't know why all of a sudden I have 4 now. With 4 dots, I can do it. Because I can find the brightest dot pretty easily, and that's definitely this one. So the side that only has 1 dot, why can't I get that 4th one? Oh boy, now I only have 2. Whatever. The side that keeps having more dots would be this one. And I don't know if that really helps. Other questions before we look at one final feature of this? Okay, there's a button on the bottom. Not a button. What do you call that? A switch on the bottom. What's that do? It's for what? Day and night. I hope it's not as clear cut as that. Well, why might we need to do it at night? Hopefully. What? No, it's important to be able to see what's behind you when you're in bed. None of you have driver's ed yet?
Have, but I mean,
Can I teach you about that?
No.
Okay. All right. Fine. What is different about driving at night versus driving during the day?
it's dark.
So what? As a result of that, what do you do differently as the driver? You turn your headlights on, right? And your headlights have 2 different settings. Yes? No? Yes. They can direct the light at a pretty low angle, well, a pretty actually steep angle, right? They can illuminate the road pretty close in front of your car, maybe 20 feet in front of your car, or you can do the high beams, and then they illuminate the road maybe 100 feet in front of your car. So that's important because you need to see more than 20 feet if you're on like a back road that doesn't have streetlights. But you can't just drive around with your high beams on, because if there's somebody in front of you, the light from your high beams like blinds them. Right? So if they're driving like towards you, that's going to blind them. Or if they're in front of you and driving the same direction as you, it's going to blind them because that's going to send a lot of light off their rearview mirror into their eyeballs. So you do this switch, which just changes the angle of the mirror a little bit. And instead of the 92% of the light, like being reflected to your eyes, you hit the switch and it moves to one of these two amounts of light. So instead of getting 92%, you're getting 4%. You can still see, but it's not blinding. It's way safer. All right, so that just changes the angle slightly of the mirror. It can tilt it a little bit, and if our eyeball's right here, it'll just direct maybe this one to our eye. Follow-up questions about that? Okay. Next, we want to use the fish tank. So I don't think you guys need to move, but I just need to change the angle of this. You're all here today, but somebody was absent yesterday and I forgot to record. That water's disgusting. All right. Not so much anymore, but we used to buy like soda in like really thick glass, right? So this is like a glass Coke bottle. You can still buy like Coke in a glass bottle, but it's just like for novelty reasons, like it's like pretty expensive to do that. We used to buy root beer in thick walled mugs, and we don't do that anymore either, right? So there's a couple of reasons for that, but I have a question first. My question is, how many ounces of drink are in each of these? Which do you think will be easier to determine, the bottle or the glass? Like, okay, all right. How many ounces? Let's get some ideas, then we'll vote. I heard 16. I heard what? 7. Okay, 16 ounces, 7 ounces. How many ounces are in like a can? I think it's 16. Am I wrong? Do we have a can anywhere? I think it's 16. What? I think it's 16. I don't think so.
16 is like the water bottle.
Water bottle.
Okay, fine. All right, Teresa, how many ounces are in your water bottle?
17.
17, fine. So more or less than that. Could we fit that whole water bottle in here? Probably. Why am I hearing like two people answer? I mean, if you don't know, I guess that's all right, but still, like, oh, I think yes or I think no. No, you're not going to do that. All right. I think yes. So let's move on to this one. More than 16 ounces, less than 16 ounces, or exactly? Raise your hand if this is more than 16 ounces. Raise your hand if it's exactly 16 ounces. Raise your hand if it's less than 16 ounces. All right. Tim said something about 12 ounces. Raise your hand if you think there's 12 ounces in here. Quite a few of you. Raise your hand if it's less than 12. One of you, two of you think less than 12. All right, Jesse, how much? 8. Teresa? 10. All right. So, is there anybody in here that thinks there's less than 8 ounces in here? Okay. So you're all wrong. What's it say? 6.5 ounces. Right? But it looks like there's way more than that because well, I'll show you that and then we'll talk about why. So I'm going to submerge this bottle into the fish tank and it's going to look really different. It looks really different, but that's actually not the whole story, right? So now we kind of get a better sense of how thick that glass is. So the Coca-Cola, bottling company, however long, 50 years ago, whenever they did this, they were taking advantage of us by giving us like more glass than it looked like and less soda than it looked like. It was pretty expensive for them to make soda 50 years ago. It's cheap now. Like they just put it in plastic because the soda is like super cheap. But 50 years ago it was more expensive, and people reused the bottles, I think. Is that true? I think you returned the bottles and then they filled them, they probably cleaned them, hopefully, but they like filled them back up. So the company made a lot more money by giving you significantly less product than you thought you were getting. Now when I dunk this in water, we're seeing some of the truth, but I'm only showing you about maybe 40% of the true thickness of the glass. There's actually less liquid in there still than it looks like now. So the reason that we're seeing more glass and less liquid is that we have less refraction going on, right? We're going from glass into water and then into air. That's going to be less change of direction than if it's going to be more of a change of direction than if we just went from glass directly into air. All right? So they used to do that to rip us off. And then same thing with the thick wall mugs. We can see that the glass at the bottom is pretty thick, but in reality the glass on all the sides is really thick also, right? And this, it wouldn't so much be the root beer company making the money, it would be like whatever restaurant or bar or whatever was pouring you the root beer, but not giving you nearly as much as it looked like. Questions about there being less liquid in these things than it looks like because of refraction, because of that change in direction as light from the liquid leaving the glass and then bending into the air. Okay, good. So now we can get rid of this disgusting water later tonight. So that brings us back to just a couple of additional comments on total internal reflection. Did we talk about the diamonds at all last class? I think we did. No, I think we actually did quite a bit. And what did we say was special about the diamonds? Very high index of refraction, right? So light goes very slow, and that made them sparkly, right? So because the diamonds have a really large index of refraction, they have a super small critical angle, like less than 20 degrees, or about 20 degrees, 24 degrees, something like that. So anytime that light is in diamond and trying to get into the air, and if it's greater than 24 degree angle of incidence, it's going to reflect back in. There's a whole lot of reflecting going on, right? If we enter light into this side of the diamond, it enters the diamond, right? Hits the air here. That's definitely greater than 24 degrees, so it reflects. That's greater than 24 degrees again, so it reflects. And now that's less than 24 degrees, so it will come back out. So typically the light is totally internally reflecting multiple times before it comes out, and that's why the diamond looks sparkly. And that's pretty, right? Diamond does that better than anything else. Cubic zirconium, which is like if you're watching like the Home Shopping Network, whatever, and you see stuff that looks like diamonds, it's probably, and they don't lie to you, they say it's cubic zirconium. But that's almost as good as diamond. Maybe instead of a critical angle of 24 degrees, it's a critical angle of like 28 degrees. So it's nearly as shiny as diamond. Other questions about diamond being sparkly because of the super small critical angle, meaning it's very easy to internally reflect. Okay. So the final thing involving total internal reflection that I want to talk about is fiber optic communications. So who does that? Who's the company that like does that? Well, Verizon does it for like telecommunications. But then I think there's probably other places that do it for like internet communication. Anybody have Verizon Fios? Anybody used to have Verizon Fios but you don't have it anymore? That's interesting. So about half of you have had it at least at some point. Is it like good? Yeah? No? Molly, no? It's just TV? So when I say is it good, like is the reception good? Is it worse than Cablevision? Is it worse than satellite dish? Is it better? Is it the same?
It's better than cable.
Same? Yesterday they were telling me that a couple of them said it was better in that like it didn't go out as much.
Yeah, like when I had Cablevision, like it would always like freeze at some points because like the reception would get all messed up, but like it doesn't really happen with Fios.
Huh. I have satellite dish now. I've never had Fios. I've had Cablevision. My dad has Fios, but I don't really notice a difference in reception. So anyway, let's talk about what the heck's going on with fiber optics. So fiber optics uses total internal reflection. We have glass fibers, like very thin, that we send light into. And we send light into it at an angle where it's not going to be less, anytime it hits the outside of the glass fiber, right, like here, we're going to exceed the critical angle. So if we exceed the critical angle, none of the light is going to refract out, right? It's all going to reflect back in. None of the light refracts out, so we do not lose any signal strength whatsoever. There are a couple of complicating factors with, all right, well, what happens if we have some light go straight through, we have others that's kind of bouncing around. There would be a time lag in getting that signal, but we have ways of dealing with that. We don't lose any signal strength, though. So we can send these signals like way further than we can using coaxial cable like Cablevision does, right? The coaxial cable does have some electrical resistance, so that's a more finite range than this. All right, so we have a glass fiber with a high index of refraction, and as we saw in that one homework question, we have a different, this is not air right on the outside of the glass fiber, it's a different transparent media, but the index of refraction is going to be less than the glass. So we actually do need to be a little bit careful about what angles we introduce to the fiber. The critical angle actually isn't that small, but as long as we don't try and do a tight curve, we should be able to keep the signal in the fiber. If we try and do a tight curve, then we're going to be bound to be less than the critical angle. So let me show you a pretty exaggerated version of a fiber optic. All right, so this is not a perfect model. Because, so what is this? This is just solid plastic. This is not hollow, solid plastic. And I can introduce a light signal right from my laser, and we should be able to get essentially all of the light to come out the edge. Like, is it pretty bright? That spot right there, is that pretty darn bright? Yeah, so all or nearly all of the light is emerging out the other end. We're losing extremely little light from the sides. Now, this is tight curves. We can't do this with real fiber optic cables because remember, real fiber optic cables have cladding on the outside. They have a relatively optically dense medium that's not air on the outside. So we'd have to do much gentler curves than having plastic directly into air. But same deal. As long as we always exceed the critical angle, we don't lose any signal strength. So a great application of total internal reflection and exceeding the critical angle. Other issues with fiber optic communications. Fantastic. So we have, well, now we actually get to start our true objectives for today. which is to talk about mirages first. So where's like the normal place that we see mirages, like here?
The desert.
Here, there's no deserts in New Jersey. On a road surface, correct. And what does it look like? Yeah, so we see a road, we're driving on a road, and we think we see water up ahead, but we get up there and there's no water. I took a whole bunch of pictures, like myself, of mirages, but when my computer got rebuilt in December, I lost them. So these are not pictures that I took, but I have a bunch of different Google search images that show us this type of mirage that Sophie's talking about. So sorry it's not too big, but we're on a road, looks like the road is flooded up ahead, but sure enough there was no water. Same thing here, this one's this one's darker somehow, but looks like there's water. When that person got up there, there was no water. Did we see that one already? No. Looks like there's water, there is no water. Raise your hand if you've never, ever seen anything like this before. 2 of you have never, ever seen anything like this before. You're not going to see it today. Maybe, I think Friday, it's supposed to get sunny again. So maybe Friday you can see it. We don't have to be in the desert to see this at all. But it really helps to have dark. It really helps to have sunny, pretty hot surfaces. What do we know about the road surface? Is what? Well, I know that at least in this part of the country, roads are dark. Right? They're made out of like asphalt, so they're typically really dark. And what do we know about like dark things? We talked about it a few weeks ago. Well, it's hot sometimes. What? Yeah. So dark things like my desktop absorbs all of the visible. If it's black, absorbs all of the visible light that hits it, and then a lot of that energy that it's absorbed like will go to increase its temperature. Right. So if it's sunny, a dark road should be pretty darn hot, right? You don't walk barefoot on the road like in the summer. If you're going to get the mail, like you put sandals on first. You don't want to walk barefoot during the day on a hot road. At night, you can do it. At night, the road surface shouldn't be any hotter than like anything else. So if it's sunny, right, we got rays of sunshine coming down, the road surface is really hot. What about the air, like maybe an inch above the road? It's going to be hot. Right? The road is radiating heat away from it, so the air right above the road is really hot. What about, not like on a 100-degree day, but maybe on Friday when it's supposed to be sunny again? What about the air maybe at like face level? So let's say it's like maybe 65 degrees on Friday. How's the air going to feel right here? Somebody said warm, fine. What if we went up 20 or 30 feet? 65 degrees is not very warm. If you had your thermostat in your house set at 65 degrees, you'd need like a sweater. So it's probably going to be pretty cool. And if we go up high enough, it's probably pretty cold. So the air temperature changes gradually as we go from this hot road surface up through these layers of air. Guess what changes along with the temperature of the air? Starts with I. Index of refraction. And this is a gradual change in temperature, so we have a gradual change in index of refraction. We won't have kinking, right? We're not just going to have a single boundary between like medium 1 and medium 2. We're not just going to have a kink, we're going to have a curve, right? So the light curves as it goes through these different temperature air, and in these inches and feet above the hot road surface, it actually begins to bend so much that it starts to come up again. So if you're walking along and you're looking down this way, right? You're looking at the road, you're gazing at the road, but you're seeing light from where? Sky. I mean the sun, sure, but for a reason. We'll talk about this in a few classes from now. The sky actually scatters light, so we only, we see light coming from the sky. So we're looking down here. We see sky at the road, but sky is kind of the same color as what?
water.